Next we will discuss theorem 18. Before going to theorem 18, we need to discuss some convention of this. If E is the subset of V star, then the annihilator E naught is technically a subset of V double star. Okay, we have discussed annihilator. If E is a subset of if first we consider for any subset S of V, what is S naught? S naught consists of the linear functionals from V to F such that uh, f of alpha equal to 0 for all alpha belongs to S. So this is the definition of S naught. If S is a subset, then all the linear functionals which sends this elements of S to 0. Okay, so this is the definition of S naught. So if we choose a subset E of V, subset E of V star, then what is E naught? In fact, this is a subset of V double star. This consists of all F from V star instead of V here V star to F such that this F of alpha equal to 0 for all alpha belongs to E. So this is the definition of E naught. Okay, so that is there is a set of all in our notation. This is all L such that L belongs to V double star such that L of F equal to 0 for all F belongs to V star E, not V star, for all F belongs to E. Okay, so this is the definition of annihilator in case of V star. Okay, now that means that technically this E naught is a subset of V double star. Okay, but we have identified V double star and V are the same. Okay, we have shown that V double star is isomorphic to V. So each element in V double star, there is an element in V, say alpha, such that this alpha is mapped to L alpha, or alpha can be identified by the corresponding L. So you can replace, so each L belongs to V double star, corresponding to each L belongs to V double star, there exists alpha belongs to V, satisfying this. Alpha belongs to V such that this L alpha of F equal to 0 for all F belongs to E. That means this is an identification of this E naught as, or E annihilator as, a subset of V. In fact, or technically this is a subset of V double star, but you can consider this E naught as a subset of V using this isomorphism. Each L belongs to V double star, there should exist alpha belongs to V star, satisfying this condition. That means you can identify E naught as set of all alpha belongs to V such that what is L alpha of F? L alpha of F is equal to F alpha equal to 0 for all alpha belongs to E. So this is one method of identifying the E naught as a subset of V. Okay, so annihilator can be annihilator of V star. Anyway, annihilator, this is a subset of V double star. Then this any annihilator of a subset of V star can be identified as a subset of V. Okay, so this identification can be concluded as a theorem if S is any subset of a finite dimensional vector space, then S naught whole naught, that means annihilator of S naught. So we start with V and a subset of Vs, then you consider S naught and again consider the annihilator of S naught itself. Then that is the null space spanned by S. So this is the This is a subspace spanned by, not null space, subspace spanned by S. So this is identification of S double naught and this S. That means likewise V double star is equal to V. We can identify S naught whole naught is equal to S itself. So we start with a subset S of V. Then W is the subspace spanned by S. Okay, that means W consists of all linear combination of elements of S. That means alpha 1, C1 alpha 1 plus etc. Cn alpha n or Ck alpha k, such that this alpha I is from S. So this is the subspace spanned by S. If this is the case, then you can easily find out W naught is same as S naught. Will you get this one? Whenever if you choose F belongs to W naught, by definition this is set of all F belongs to V star, such that F of alpha equal to 0 for all alpha belongs to W, and if you choose such an element F from W naught, then you can get F has this property. Then we will prove that S has that means F maps every element of W to 0. Okay, so in fact this F maps alpha 1 equal to 0, alpha 1 equal to 0, F of alpha 2 is equal to 0, or equal to 0 for all alpha 1, alpha 2, alpha I belongs to S, because this contains the linear combination of. So anyway, S is always a subset of W itself. Every element of S is a element of W. Then whenever F sends every element of W to 0, then F sends every element of S to 0 as well. So this shows that this F belongs to S naught. On the other hand, if you choose an F from S naught, then what is the importance of this? S naught is set of all F belongs to V star, such that F alpha equal to 0 for all alpha belongs to S. Okay, now you consider an arbitrary element of W. Then what is F of C1 alpha 1 plus etc. Ck alpha k? So this is equal to C1 F of alpha 1 plus etc. Ck F of alpha k. Consequently, these elements are 0, because these alpha 1, alpha 2, alpha 3 are elements of S, and F belongs to S naught. So these are all 0, then you can get this equal to 0. So this is for every C1 alpha 1 or every arbitrary element, any arbitrary element of W. So belongs to W. So this shows that F belongs to W naught. That means the reverse inclusion is also true. That means W naught is same as S naught. So whenever we consider a subspace spanned by S, then the annihilators of those two, this is a annihilator of S, and this is annihilator of the subspace spanned by S. Both will be the same. Then you can easily, once you identify this, then you can easily prove that theorem. That is, W is, we need to prove that W is the subspace spanned by S is this S naught whole naught. What is S naught whole naught? S naught is same as W naught. So we need to prove that W naught whole naught is equal to W. So it is enough to show that instead of showing S naught whole naught is equal to W, we will show that W naught whole naught is equal to W. That means W double naught is equal to W. So that is so trivial because we have already seen that dimension of W plus dimension of W naught is equal to V. Okay, and if we apply this to W naught, then dimension of W naught plus dimension of W double naught is equal to dimension of V star. This is the domain is V star, but we know that these two quantities are same. Dimension of V and dimension of V star are same. So we can get this dimension of W equal to dimension of W double naught. Okay, but we know that W is a subspace of W naught because if you choose any element belongs to W, if you choose any element, this is the mere identification of W and W naught, W double naught. This is because if you start an element alpha belongs to W, we need to prove that this alpha belongs to, instead of proving alpha belongs to W double naught, we will prove that the corresponding L alpha belongs to W double naught. This is the requirement. Okay, so first because we identify this alpha as L alpha in W double V double star. Okay, so this W double naught is an element of V double star, subset of V double star. So alpha belongs to W. Then you consider L alpha belongs to W double naught. That means L alpha. What is L alpha of F for F belongs to W naught? This L alpha of F is equal to F of alpha, where F belongs to W naught. And we know that if you choose an element alpha belongs to W and F belongs to W naught, then this quantity is always 0. That means this L alpha of F is equal to 0. This is true for all F belongs to W naught. That means L alpha sends every element of W naught to 0. That means L alpha belongs to W double naught. So whenever you have alpha belongs to W, then you can get L alpha belongs to W double naught. If you identify this L alpha as alpha, then you can say that alpha, the corresponding element of alpha, is also in W double naught. So this implies this one. That means W is a, in that sense you can say that W is a subset of W double naught. That means dimension of W and dimension of W double naught are same, and we have one inclusion. Then we can say that these two subspaces are the same, up to some kind of isomorphism. Okay, so this proves the theorem 18.